Welcome to qiphyedu. Today we'll be looking at Computer Science Paper 12, October-November 2021. Alright, let's start. Okay, so for the first question, we need to draw one line for each measure to indicate whether it keeps data secure or protects the integrity. So here we have 5 measures. The first one is firewall, second one is double entry, and then presence check, access right, and password. Okay, so now let's take a look at what all these are related to. So firewall, it's a means of protecting your computer from malware or viruses. So this falls under security. Okay, so I'm just gonna put a mark there. Okay, double entry is a form of verification, which means that once you type in, let's say for example, you type in a password for the first time, you type in a second time to verify that the previous password that you typed in is the same as the password that you typed in the second time. So that's to ensure that the password typed in is the same as the previous one, basically. So this comes under data verification. Okay, presence check is to check whether your data is typed in or not. So this is under validation. And then access rights is basically to restrict the types of data that a person can see. For example, like let's say I have a big database with a bunch of tables. I only want this group of people to look at maybe table 1 to table 5. And then for this group of people, I only allow them to look at table 1 to table 7. Probably because table 6 and table 7 is related to their job scope. And then table 1 to table 5 is for everyone else. So this comes under data privacy. And then password is to prevent unauthorized access to your devices. So this comes under security. All right. So now let's look at this. So data privacy and data security comes under data security. So firewall will be linked to data security. And then the double entry, since it's under data verification, it's under data integrity, because data integrity is to ensure that whether the data typed in is relevant or not. So this goes to the second one. And presence checks is the same thing as well. And then for access rights, since it comes under data privacy, that means it goes to data security. All right, and then for password, that'll be the same thing as well, also under data security. All right, so that's for this question, and let's move on to question 2. Okay, complete the truth table for each of the following 2 logic gates. So as you can see, we have this is a NOR gate. So I'm gonna write here NOR gate, and then second one is a NAND gate. Why is it NOR and NAND? Is because there's this circle after the gate. That means that you're changing the values to a negative to the opposite number. So instead of 1, you get 0, or instead of 0, you get 1. Basically, that's the case here. So it's a NOR gate and also a NAND gate. All right. And then so let's see. So whatever, if let's say like if it's for OR gate, whatever the value is in OR gate, it will be the complete opposite around. So for example, 0, if it's 0 or 0, if it's 0 or 0, suppose it should be equals to 0. But because it's NOR gate, it's the opposite. Instead of 0, it's a 1. So here it's a 1. And then for 0 nor 1, supposedly 0 or 1, it's 1. But the opposite would be 0. Same goes for the third row. And then for the last row, supposedly 1 or 1 is 1. But because it's the opposite, so it's 0 as well. So it's 1, 0, 0, 0. For NAND gate, let's just think of it as N. So 0 and 0, we get 0. But the opposite would be 1. So the output would be 1. And then 0 and 1, we'll get 0. Same goes for the third row. Right? Supposedly we should get 0 as well. But because it's the opposite, it's also 1. The third row will be 1 as well. And 1 and 1, we should get 1. But because it's 1 and 1, so it's 0. Right? So this is how you get the answer for question 2A. And then for question 2B, we need to draw a logic circuit for the following logic expression. Not A and B and C. Okay, So A and B. So now what we need to do is we need to draw an AND gate. Now keep in mind that this is not NAND gate. Like instead of NAND, it's not something and something. So do not try to draw an AND gate and then a circle on the right hand side of it. This time it's actually wanting you to draw an AND gate, and then only then you link it to a NOT gate, right? So you have to link it like that. So here, so it's now first we need to draw we need to draw A and B first. So A and B. So let me draw a line here. Okay. Okay. All right. Actually not because okay. Oops. All right. So now draw the AND gate. Something like this. So now it's A and B. So before we link it up with C, we need to first link it with a NOT gate, right? Okay. And then C, then we need to link it with AND gate. Okay, and then the last one would be this one. So you need to bear in mind that the not A and B and C, we need after we draw A and B, we need to link it with the NOT gate because it's something like this, and then we link with C, and then here we need to draw another NOT gate. Just gonna copy and paste from the previous one, make it easier. Right, and then we link it to X. But you can see that because of the way I draw, I need to link it using a few more lines. So it'll be something like this. Right. Okay, now I move on to question 3. So Andy likes to play computer games and he uses several input devices. These include a keyboard and a microphone. Describe the principal operations of microphones. First, we need to talk about the characteristics of the microphone. First of all, we can say the microphone has a diaphragm. And then we can say the incoming sound waves cause vibrations of the diaphragm. Causing a magnet to move. And when that happens, an electrical signal is produced. Okay, so this is how you get your 3 marks. You just need to write 3 things. Basically it's 4 things, but I'm just gonna count as 3. Microphone has a diaphragm, and then like when you're talking to the microphone, it will cause there'll be vibrations on the diaphragm, and then the vibrations would cause the magnet to move. When the magnets move, there'll be electrical signal, and then that's how the sound is recorded. How the sound will then be moved over to the computer, right? And B, so you play some computer games on the internet. He has several devices that connect wirelessly to the router in his house and define the topology. So for most of us, especially for home networks, we have a router, and the router connects to, depends on what router that is. It can be a DSL connection, it can be a fiber connection, but mostly a fiber connection. So it connects to the internet using that. And then the router will then link up several devices wirelessly or on wire connections using the Ethernet cable. So mostly for house networks, would be star topology. We can say reason for that is all devices only connected to the router. Alright. Then for B2, the router has a wireless access point to allow the devices to connect wirelessly. Identify 3 functions of the router in ND's network. So what does the router do? The router, some of the main functions of the router would include to send and receive packets from devices or to the internet. Okay, and then to find the destination of the packet. We can also say to allocate private IP addresses to devices on LAN. I have to click this off. Yep, something like this. So first of all, you can say to send and receive packets from devices or to the internet. So we receive packets from devices and then send the packets to the internet. And then it's used to find destinations of the packet and also to allocate private IP addresses, because a router has a public IP address, and that is what is being actually all devices have a public IP address and a private IP address. And then the router will then assign a private IP address for the devices. Okay, so all devices, each and every one of them will have a private IP address, and this is done by the router. Okay, and then for question 4, okay, there's a binary number, and the binary value in the register represents an unsigned binary integer, which means that this is a positive number. Regardless of whether there's a 1 in front or not, it will still be a positive number. Convert the unsigned binary integer into denary. Okay, so we start from the right, that means 2 power of 0 until 2 power of 7. Okay, so 2 power of 7 will be 128. 2 power of 6 will be 64. And then this is 0, so we can ignore that. And then this one is 2 power of 3 will be 8. 2 power of 2 will be 4. And then 2 power of 0 will be 1. So after calculation, that would be 205. So that's the answer. And then the binary value in the register represents a 2's complement binary integer, and convert the 2's complement binary integer into denary. So now it says that it's a 2's complement binary integer. So now this 1 will determine whether the number itself is a positive or negative number, right? So because it's it's already a 1. That means that it is a negative number. So now we need to convert the 2's complement binary integer into denary. But before we do that, yes, we need to convert it like from a negative number to a positive number. So here, I'm going to convert that. So that would be 0, 0, 1, 1, 0, 0, 1, 1. Right, so this is the positive number. So I'm just going to add it up. So here from the left, you'll see that there'll be 32 because of 2 power of 5, and then plus 16, and then plus 2 plus 1. So we will get 51. And then we need to add a negative sign to the front, so that will be negative 51. Right. The binary value in the relation represents a hexadecimal number. Convert the binary number into hexadecimal. Okay, hexadecimal, we need to look at it, split into half, and then we count. So this one would be, for me, what I do is I just, I'll just, okay, we just have to erase out these things here, because since we already split it into 2 halves, that means that starting from, that means that every number, the maximum number would be 16. So it would be something like this. And then this one would be 12. And then this one would be 13. But there is no way that you can represent the character with 2 digits. It must only be 1 digit or 1 character. So starting from 10, that would be A. So 10 is A, B is 11, so C is 12. Okay, and then for 13, that would be D. So the hexadecimal value would be CD. And then state why the value in the register cannot be interpreted as a binary coded decimal. So why it cannot be represented in decimal? Because binary coded decimal, that would be if let's say you need to, if you need to interpret it as a binary coded decimal, it must be represented in digits. It must be digits. So in this case, you realize that for each each group of 4 bits, it already exceeded 10. So you can see that it's 12 or 13, which is not something that binary coded decimal is designed to be in use for. So binary coded decimal is to basically show 2 digits, but then it must be digits but not alphabets. So here we can say that denary value in each group of 4 bits is greater than 9. So this is the answer for that. And then E, the binary contents of 2 registers are these numbers, and then add the content of register 1 and register 2 together. Show it working. So I have to show my working, so I'm going to draw that here. Okay. So move it up a little bit. Okay, so we start from the right. 1 plus 1 is 0. We move the 1 to the left. So here we got 1. And then 1 plus 1 is 0. So we move the 1 to the left. So here we get 11 because of 3 1s. So 1 we move to the left. So 1 plus 1 we get 0. Move 1 to the left. The first 11. So what we get is 0, 1, 1, 0, 1, 0, 1, 0. So this will be 0, 1, 1, 0, 1, 0, 1, 0. Here's the answer. Okay, so for question 2, we need to subtract the contents of register 2 from the contents of register 1. So register 1 minus register 2. So this will be 0, 0, 1, 1, 1, 1, 0, 1 minus 0, 0, 1, 0, 1, 1, 0, 1. So what you get is 1 minus 1, 0, 0. Everything here on the right will be 0 until this bit. 1 minus 0 will be 1. And then the left one will be 0, everything is 0. So now we'll have 0, 0, 0, 1, and then 0, 0, 0, 0. So this is the answer. You could also do it the other way around for this question, is by changing the number in register 2 the numbers in there to become 2's complement, and then you put a plus sign, and then you can plus the numbers together, and you get the same answer. Okay, number 5. Ria has created the following logo as a vector graphic. Complete the table by writing a description of each vector graphic term and give an example for this logo. So the term property, what does that define? That defines data about the shapes. Data about the shapes. Like for example, a solid fill, a black line. We can just say black line. Drawing list would be the list of shapes that's in there. Okay, for example, this would be like a rectangle, right? B, Ria takes a photograph using a digital camera. The photograph is stored as a bitmap image. Describe 2 differences between a vector graphic and a bitmap image. So, okay, the first one we can just say bitmap is made of pixels. Whereas vector graphics are made up of shape of a set of instructions, a set of drawing instructions, a set of we just say instructions then. And then you can say that bitmap files are usually larger. Than vector graphics. Because data of each pixel needs to be stored in a bitmap image. But for vector graphics, only the drawing instructions are stored. Right, so this is how it get 4 locks. And then 2, the Ria needs to email a photograph. She compresses the photograph before sending it. So describe 2 loosey methods. So here the main point will be 2 loosey methods. So this would be reducing bit depth. And then we can say reduces number of bits per color, right? And then we can just say number of bits per pixel because that makes more sense. Like number of bits per pixel. So like supposedly for, let's say image supposedly it will be 24 bits. We can compress it to 8 bits. So the colors that are stored in 1 bit will be lesser. Method 2 will be to reduce the resolution. Decreases pixels per inch, which decreases size of binary. Right, so that's how you get 2 methods. You need to first say the method and then explain how does it work. Okay, question 6. Shop sells plants to customer. The shop manager has a relational database, so we have 4 tables, right? And data is now trying to be normalized. So there's 3 stages of normalization, which will be first normal form, second normal form, and third normal form. So we need to remember that for second normal form, there's no such thing as partial dependencies. Okay, I'm just going to put depend because of lack of space. Third normal form, there will be no transitive dependency. Okay, so here we look at the first task is remove any partial key dependencies that will be from first normal form to second normal form. So this will be here. Removing any repeating groups or attributes, that would be the job of zero normal form to first normal form, which is to remove any attributes that are being like repeated. Like for example, let's say there's one table where there's this field with same data and all those, that will be removed. And then for second normal form, the third normal form, which will be removing any non-key dependencies. So that would be for the normal form. Yep. So this is how normalization is done. And then now we need to draw an entity relationship for the database plant cells. So here you can see that for purchase item, the foreign key is plant name, which means that in order to get information for plant name, it needs to link to the plant table. All right, and then the primary key for purchase item is purchase ID, and it links with the primary key of purchase, which is also purchase ID, like so. And then customer ID is the foreign key of purchase, so it links with customer table. So now we need to start from plant to plant name. So for one plant, there would be many purchase items. So it'd be like this. One to many. Oops. And then plant name, I'm link to purchase ID, purchase item to purchase. So this would be so one purchase can consist of many purchase items, right? So we can draw something like this. I'm not sure if this can be rotated. Yeah, I don't think so. Right. Then it'll be something in this. There's something in this. And then purchase to customer. So one customer can have many purchases. So you can see that the customer ID is now moved to as a foreign key for purchase. So one customer can have many purchases. So you can do something like this. Right. So this is how you draw the entity relation diagram. And then B, the shop manager uses a database management system. Describe the purpose and the content of the data dictionary. The data dictionary is used to store metadata about the database. For example, the table name, primary keys, and relationships. Okay, then for C, the shop manager uses both DDL and DML statements to create a search database. Complete the DML statement to return the total number of items purchased with the purchase ID of 3011A. So now we look back here. So you can see for purchase item, there's a quantity, purchase ID, and plant name. So now what we need is we need to return the total number of items purchased with the purchase ID of 3011A. So the table that fits this purpose will be in purchase item. So here we just say select some quantity, okay, from purchase item. It should be something like this. And then we can say where, well, because there was already a purchase ID in there, so purchase ID equals 3011A. But then this one we need to have open, we need to have this quote or end quote, and then write DDL statements to include a field in the table purchase to store the data of the order. So we need store the date of the order. So for question 2, we need to write DDL statements to include a field in the table purchase to store the date of the order. So now we need to alter our purchase table. So here in this purchase table, there will be a date like so. Or you can just write whatever name you want, but just have a date. So here, but then because it says date of order, so I'm just gonna, okay, we can change it to date of order. And then let me alter table purchase at date of order. And then the data type would be date. And then semicolon. So that's the DDL statement. 7, a computer has system software. The operating system handles interrupts. Tick one box in each row to identify whether each event is an example of a hardware interrupt or software interrupt. So if let's say the buffer is full, this is under software interrupt. If printer is out of paper, this is when paper is gone, so this will send a response to the printer, and then the printer would then send it to the computer. This is under hardware interrupt. User press a key on the keyboard, so it's pressing the hardware, so it's hardware interrupt. Divided by 0 is based on software, so that will be software interrupt. Power phasing is because of hardware, so it's here. And then stack overflow is because of a program, so it's under software interrupt. And then describe the file management task and operating system performs. So you can say that, okay, it's a format question. So storage space is divided into okay, and then we can say space allocated for particular files. And then we can say that it specifies logical method of file storage. And then controls file access. Not only that, it specifies the task. That can be performed on the file. Normally that will be like copy or cut or paste. Okay, something like this. Identify 2 utility programs that can be used to improve the performance of a computer and say how they improve performance. Okay, defragmentation. It arranges files. To make them contiguous so that there is less head movement. And 2, we can say this cleanup, which cleans up the unwanted files. on the hard drive. Okay. And question 8. The von Neumann model for computer system uses registers and describe the role of the following special purpose registers in the FE cycle. Memory address register stores addresses that would be fetch later, and later, which is held in the program counter. Memory data register, it stores data from address pointed to by the memory address register. Data is then copied to the current instruction register. And then 2, another special purpose register is the index register. And if I want another special purpose register used in the von Neumann model for a computer system, that could be the program counter, another one would be the current instruction register, then there could be the status register as well. So we can just say, whenever we want, we can just say like program counter. Alright. And then for B, so we have this table, and then now we move on here. In the following table, each row shows the current contents of the ACC in binary and the instruction that will be performed on those contents. So current content of ACC is 0101001. Instruction is XOR 101. So now we need to convert the data in address 101. Actually, no, the data is already there. It's 11111000. So we just put it here. And it's XOR. So let's see what's going to happen. So 1 XOR 0, we get 1. 1 XOR 1, we get 0. 0 XOR 1, we get 1. 1 XOR 1, we get 0. The same goes for the right. So that will be 0101. Okay, so this would be 1010 and 0101. This one is N104. 104 is all ones, so we just put it here. But honestly saying, we can already see the answer directly from here. The answer will be all 10000. For LSL4, this means we need to move 4 places to the left because it's L, which means left. So we move it 4 places to the left. That means that the 4 zeros on the left will be eliminated. It will become 111. So here will be 1111. And then we need to introduce zeros on the right. So it'll be something like this. And then here on the bottom, it says all 102. 102 would be 4 zeros and 4 ones. So we can just put it here. But in this case, the answer would be all ones because 100 will be 1. So then it goes for everything on the right as well. So this would be 1111, 1111. Alright. Here, the following table contains 5 assembly languages and instruction groups and one appropriate assembly instruction for each instruction group. So here, input and output data will either be in or either be out. Okay, you can write like that. And then for arithmetic operations, like for example, increment or decrement. But then thing is, we need to follow the instruction set. So here we have increment. So we just put the INC. It can be INC-IX or INC-ACC. And unconditional and conditional instructions, that would be like JPN or JMP. JPN would be when it is false. So we will jump to the jump to the address if it's false. That JPE would be true. And then if it's unconditional, it'd be like directly jump. So that'll be like JMP 100. And then compare instructions, that will be CMP100. Or it can be anything else as well. But just using this example, compare instructions, so it's CMP. All right. And then, okay, so I think this is the last question. LDM uses immediate addressing and LDD uses direct addressing. And there's another form of addressing, so we can just say index addressing, which would be also another mode of addressing. So I can say that forms the address from a given address plus the value in the index register. So for this type of index addressing, it would be like something like this. Let's say we have a base address, like we have LDX, maybe 100, and then we need to plus the value in the IX. The IX may be 5. So 100 plus 5, we get 105. So we need to reference the value inside address 105. So that's how we get the value for LDX 100. Instead of getting the value inside address 100, we get the value inside 105 by adding in the value of the index register to the base address, right? So that's for index addressing. There's also another one called indirect addressing. So the address that you need to be used is at the given address. So like the address that is given, you need to look at the value of the data that is inside that address, which will give you the address that you need to reference the data to, right? So for example, let's say I have like indirect addressing, like for example, I got LDI 100. Then the value in 100 is 105. Then I need to reference the data in 105. Let's say the data in 105 is 20. So the value that I'll get at the end will be 20. Yeah, this is how indirect addressing works. And then there's another one, which is relative addressing. So relative addressing, the address that is used would be like a number of locations away. So you need to have the base address plus the offset. Okay, so instead of like maybe 100, you need to add like the offset value. So you get, instead of like 100, you maybe you add like 4 or 5, you get 105 or 106, something like that. Then you can get the data. So this is how relative addressing works. And yeah, that's it for this paper. I hope that you'll be able to learn something from this video. And if you have any comments or suggestions, please comment down below, and stay tuned for more past year papers and explanation videos. Until then.